Welcome everybody to Radio Telescope Observation Party. This is the once in a month SARA holds a observation party, and in 2 weeks we hold Drake's Lounge, which people can present both observations, but a lot of that, the Drake's Lounge usually delves into the technical issues of building your telescope, getting things tuned up, etc. And then usually the week after is the fourth Friday of the month is Drake's Lounge Australia, in which we get our Southern Hemisphere friends to tell us what they're doing and get that organized. Little pre-advertisement about the the Eastern Conference. I think you saw that when I posted that. Is that on June 7th to the 11th is the Eastern Conference in Green Bank. It's going to be a joint conference with the Radio Jove team, who we've been working with forever. And we actually sell the Radio Jove devices through our store. And they'll be presenting. I think they got 5 or 6 presentations already lined up. And so they'll be presenting. And then we'll get then we'll have a bunch of our presenters. We are looking for some presenters now, so if anybody's interested in presenting their findings, there's like time slots between 15-minute and the full time slot is a 40-minute. And Marcus Fisher is the vice president in charge of the Eastern Conference this year. But you can send a note to me or in chat even here that says you're interested in presenting, and I'll hook you up with the coordinator. Okay. I don't have anything else. Let's see. Let's go with Ted. Let's go with you first. Is you warmed up?
I guess I'm here. Yeah. Okay. But I have nothing really to report. I'm eager here to see what other folks are doing. I may have strong opinions. Thanks.
Okay. All right. Let's go with Wolfgang.
Yes. Well, I can report or tell a little bit about an experiment that we did on the 22nd of March. At that time, we had an inferior conjunction of Venus, which means it was close. And we did something which we normally don't do. That is, go away a bit from the astronomy side and go a bit into somewhere in between amateur radio and astronomy. So I have just 2 slides which I can show. Let me do that. Okay, can you see my full screen now? Okay. So this was an experiment to send a signal to Venus and receive it. And actually, we have no transmission capability. So the transmission was done by the Dwingelo telescope, which is also a 25-meter dish operated by cameras, also a group of volunteers. So I have to say, and I have to give credit to them because they really did all the heavy lifting, like setting up.
Sorry. Okay. I was mentioning that the team in the Dwingelo did the difficult part. Also, they did a lot of the necessary calculations and so on. But just to still visible, just a few parameters. At the time, the distance from the telescopes to Venus was about 41 million kilometers, which gives us an apparent size of 0.018 degrees on the sky. Venus is actually similar in size to the Earth. It's just a little bit smaller, but about roughly the same size. That distance gave us a round trip time of about 280 seconds. And the people in Dwingelo, they had a transmitter providing 1 kilowatt power. They had to get special permission from the regulator because that's normally not permitted in Europe to use that kind of power at that frequency. Also, that permission came with a limitation. They could only use it for 2 hours. But anyway, they had the permission. The frequency used was 1299.5, so in the amateur radio band. One of the challenges there is the Doppler shift and the variation of the Doppler shift. The background is that you have essentially a very weak signal, and the intention was to have that signal in a small bandwidth only, which means we tried it with a carrier, and we needed to make sure that we only take the bandwidth that is needed to detect the carrier, which was less than 1 hertz, which also means that your frequency accuracy had to be very high, and you had to account for the Doppler shift, in this particular the changing of Doppler shift. So during the experiments, the Doppler shift changed, and that was also dependent on the location, depending on whether the reception was done at the Stockard or at Dwingeloo. And you can see the numbers here. That's different for the 2 telescopes when they receive. The whole exercise required a fairly high frequency accuracy, so in order to keep it within 1 hertz of bandwidth. The expectation was that it would be pretty much at the limit, given the efficiency and the size of the telescopes and also the transmit power. We said before we did, well, maybe we see the carrier, but maybe not. And this is what we actually got. There were 4 transmissions. Each lasted for 275 seconds. So for 255 seconds, the carrier was sent out. It was just a little bit less than the round trip time, so that Dwingeloo themselves could receive the signal. So they sent it out, and while the signal was on its way, it continued transmitting. But when the signal was expected to be back on Earth, they stopped transmission. And you see 3 panels there. This is actually the received signal in the channel where it is supposed to be. And as you can see, it was exactly on the frequency. So it was a pre-calculated Doppler shift, and it was exactly where it was expected, within a hertz. The signal-to-noise ratio at Dwingeloo itself was such that it was a 7.1 sigma detection. On the Stockard reception side, we're somewhat more sensitive, even though the dish size is about the same. And we had a 10 sigma detection. And if we combine both, it's getting even better. So the signal was maybe slightly better than we had hoped. The one uncertainty was how much Doppler spread we would get from the Venus. As the Venus also moves and jiggles a bit, we expected that there would be some broadening of the spectrum, but it actually was not. So that was fortunate for us. Yeah. While we were doing this, there was also an attempt by the DSES group. They were also setting this up on a slightly different frequency, but we were monitoring both frequencies. Unfortunately, their transmitter failed after a short time. So they sent for 3 minutes, and then unfortunately the transmitter failed. And actually the same happened to our guys, our friends in Dwingeloo. They had 4 transmissions, and as they wanted to continue, also the transmitter failed. So there was somewhat a limitation. Coming back to DSES, we recorded their signal, but we could not detect any signal back from Venus. Maybe that's quite likely that simply the integration time was too short. We just had a little less than 3 minutes. Okay, going forward, we think it was a nice experiment, and this has not been done in a long time. So it was fairly new in the sense that it was yeah, I think it was 15 years ago when it was done the last time before. We are hoping that we can repeat the experiment in October of 2026. That's when the next inferior conjunction will be. So we are preparing for that, hopefully in time, so that we can repeat that. Okay, that's all I can report at this time. So if there are any questions, below you see the large number of names from the cameras, which is a Dwingelo team, which did all the heavy lifting on this project. And I'm really, I shouldn't say it's our experiment. It was more a Dwingelo experiment than ourselves. We were supporting it with our a very good reception capability. Okay, I'm happy to take questions.
Wolfgang, you talk about a conjunction so that we're close, Venus and Earth are close to each other. How important is that?
We can move on.
I'm asking how important is that conjunction? Is the distance that important to us to do the experiment? I'm asking how important is that conjunction? That's the point where Venus and Earth are close together. We really need that advantage?
Yes, you need that. The reflection back, the power of the reflection back goes by the fourth power of the distance. So it rapidly declines as it gets further away.
And so I have a question or comment. First of all, congratulations on this effort for you and the other folks as well. But I guess since you got the frequency exactly right, it just says all the calculations on the orbital mechanics were exactly on target, which was very interesting. It sort of confirms a lot of things. But I noticed you also have a little spike just to the right of the main signal in your spectrum. And I wondered if you knew what that was.
Yeah, I was wondering about that as well. Let me bring that up again.
Maybe it's your local oscillator, and that's just a difference in the frequencies, I guess.
I think you're referring to this on our reception. It's not true. Yeah, you could argue that, no, not really. In the Dwingelo signal, it's not there. And on our side, there's something to the right. I think this is just because it's below 4 sigma, it could be just the noise peak.
Okay.
Because we are pretty confident that on both sides, the frequencies were very accurate. We have done some tests before that. We did some EME things, just testing the coherence of the frequencies. The Dwingelo, they are actually tied to the hydrogen maser from the Westerbork telescope. We're not as good. We have our rubidium, but it's also checked, and we did some checks on that. So I don't think we had any change in the frequency. And you're right, the accuracy of the calculation, that was really amazing because it came out to the hertz. And it also, what we needed to take into account is the variation over time, because it changes with, if I recall correctly, 0.2 hertz per minute, I think. So we need to take that into account as well.
Impressive work there.
Got a quick question, and depending on the accuracy of your receipt, can you tell the distance that the actual time difference related to the distance to the to Venus at that time? Can you tell if how close that was to your predicted, and you have enough accuracy to determine how far above the center of the Venus you were actually reflecting on, because it's supposedly the clouds you're reflecting on, not the surface.
Well, as far as I know, you're actually reflecting from the surface. At least that's what the let's say radar suggests. From if you look back in the history, these Venus radar experiments, these were performed in the 60s originally, And nowadays it's done by spacecraft which actually are close to Venus. And since you can see with the radar from the spacecraft, you can actually see features of the surface. So it seems that the reflection is actually coming from the surface. What you do have is that there's a certain time delay between signal which is reflected from or the center of Venus and or from the sides. This is quite apparent when you do that same experiment on the moon. But we haven't seen much of a time difference there, simply because we took a long integration time. So we have minutes of integration time. So any variation in the time reflection would not show, and that doesn't change the frequency.
All right, thanks. Good work.
I have a quick question. Has there been any explanation released as to why both transmitters failed?
The word that I have is that at DSCS, the reason of the failure was that there was a when the transmitter heated up, an additional fan kicked in. Unfortunately, that fan created a short circuit, so one of the power supply went down. So there was a short circuit, and on the Dwingle side, there were some transistors in the end stage blown up.
I'm
So
curious. The earlier initial, I believe that was back in something like 2008, where the initial amateur signal was bounced off of Venus, and I think that was using a significantly higher power. I think it was a magnetron that had 4 to 5 or some odd kilowatts. And
yeah,
what kind of permission did they have to use that kind of power? And is it possible for the next conjunction to have a transmitter with more power output?
Obviously, at the time it was done by Bochum, and I think they used 6 kilowatt, and also they had a higher frequency. I think they were in S bands, which gives a narrower beam. That also helps. In any case, you need to have a special permission from a regulator. It was not the case that Dwingelow, the guys did not. They simply had a 1 kilowatt transmitter available, so that's what they asked for. Maybe in 1.5 years, there may be a higher power transmitter, and hopefully they will get the permission as well. But that has to be seen. I mean, I personally cannot really comment on that on the transmitter side, because we are at the Stockard, we are not doing any transmission in that frequency range. The only thing that we do is EME in the 12 gigahertz range. So this is where we have some capability, but of course at 22 gigahertz with 75 watts, so I think that's the power that we have, you can't reach Venus. So
Yeah,
essentially
thank you.
our role is on the receiving side.
Yeah, well, that was a fantastic effort. Really, congratulations on that work.
All right. Any other questions for Wolfgang? Okay, thanks. All right.
Thanks.
Rob Lucas. And he's currently in Australia, so this is the middle night for him, or the morning.
It's really dark outside. Well, I don't have anything new to report except I've fired up the computers and the two antennas are working, and we'll see what we capture for data. So I don't have any new analysis or anything to actually report. So I guess that's basically it for me. Go ahead.
Thanks, Robert. Let's see. Edward.
Hello, hello. Can you hear me?
Yep.
Good. Yeah, so I also don't have a lot to show this time. Not any very exciting new observations or anything, because, well, here in the Netherlands, we have had a very unusual period of clear skies. So, and besides radio astronomy, I also do optical astronomy as well. as in the visible range of the electromagnetic spectrum. So I've been just playing a lot with my optical telescopes, just doing some observations and astrophotography. We also had a partial solar eclipse here last week, so that was also very nice. But yeah, I haven't really done a lot of radio astronomy recently.
Okay. Well, we'll forgive you for doing optical for this one time, but get back to the science.
Well, I actually do have some observations from late February, begin March. Maybe I can show that. Let's see. Open this. Share screen. You see this?
Yep.
Okay, great. Well, yeah, so back in February, I visited Astropeiler, and Wolfgang there was doing some observations of water masers. So yeah, as you may know, I also have a small setup for water masers, 1 meter dish. So recently did some more or less routine observations. This is becoming more routine now. So this was Cepheus A. So nice peak at minus 10 kilometers per second as expected. With not much special things going on here. Then can I go to the next? Orion KL. So this one was a little bit weak, so it was a bit more difficult to detect. Westerhout 49, so I've been tracking this source for quite some time. I also showed an animation actually of the spectrum from the last couple of years during the Western Conference. So currently there's not a lot going on here. There's some minor changes in the spectrum. So this was from 28th of February, and this was from March 31. So you can see between the two dates, yeah, the spectrum shifted a bit, but that's because I tuned the SDR to slightly different frequency. Yeah, there's not a whole lot of change. It seems like this little peak is getting a little bit weaker. Oh yeah, and this was Westerhout 51 from the 2nd of March. And finally Westerhout 75. What I found quite interesting about this is that normally I can easily pick up the main peak at 10 kilometers per second, but I also detected some weaker signals at some other velocities. So at around 11 to 12 kilometers per second, there's a small peak. Another one at plus 4 kilometers per second, and there seems to be another one at around minus 10. And yeah, these are all also visible at on a different spectrum that was made by Astropeiler last winter. I don't remember exactly which date, but Wolfgang sent me a couple of spectra from some of these water maser sources that they observed recently. So just for comparison. Anyway, so that was all I did for this month. Are there any questions?
Now, these were all water masers, right?
Yes. Yeah.
And how long did you and this is just for the people that are on that haven't seen this before. So 1 meter dish tracking, or is that what you're using, and how much integration time and frequency?
So this is all at 22.235 gigahertz, which is the frequency of the water masers. So I'm using a Norsat 9000 LD LNB to receive at this frequency. And the integration times, yeah, usually 1 to 2 hours.
Okay. All right. Thank you. Good work. All right. Let's see. Dmitri.
Hi to all. Today I have some news about uh, pulsating maser G107. Just a moment. Some news, some info update for this maser, including results of observations and some thought about possible observations of its hydroxyl line. This is pulsating maser with defined period 34.43 days. This maser seen in methanol 6.7 gigahertz and maybe other lines in water 22.2 gigahertz. Also hydroxyl lines observed by they are rather weak. In mid-February, I told about 6.7 gigahertz maser expected in March 12, but this was not quite correct. Accurate calculations give midnight March 10 to March 11 peak of this maser in 6.7 gigahertz. This is crucial for observations because 6.7 gigahertz line is very sharp for methanol. This is very interesting object. Intermediate mass young stellar object with still not blowing away its molecular cloud and dust. Maybe this is rotating binary system modulates this maser pumping or seed photons. You can see sharp type diagrams of this maser. You can see sharp peaks of methanol masers, less sharp peaks of water masers, and some peaks of hydroxyl masers. How sharp methanol peaks you can see well in Japanese IMET data, 6.7 gigahertz, very recent data. Last point in this plot is January 25. Sharp peaks detection is sensitive to the data rising and falling of peaks is about 3-4 days, as you can see from this plot. Lines expect lines in water. Here velocity for water lines is about minus 16 kilometer per second. For methanol is about minus 7.5 kilometer per second. Also, I inserted hydroxyl lines info minus 12 kilometer per second. You can see here, and levels about 1 to 2 Yatsky for 1665 megahertz hydrox. About water observations, Wolfgang and Edward did not see it, report that not detected for astropillar dish 10 meters. Although water line is expected less sensitive to date errors, as you can see on this plot, 22 gigahertz. Not so sensitive like 6.7 gigahertz. Next, correlations between 6.7 gigahertz radiations and infrared radiations. Correlations is seen and observed between infrared and methanol radiations. Next, this is map of this maser. You can see it says the star in the center is still existing continuum, 1.3 millimeter continuum of hot gas. You can see circles methanol masers from and water masers. Intensity here you can see value of intensity here on the plot. Dash line molecular overflow still process of blowing away clouds has begun. You can see lines of molecular overflow. 6.7 gigahertz observations, instrumentation dish 2.4 meters. System equivalent flux density is about 1.4 tenths and fifths obtained by solar measurements. You can see details of how extract the CFD in forthcoming issue of the journal. Some article I hope will be published. Minimal detectable peak flux density was 57 Jansky with integration time about 2 hours, resolution 5 kilohertz. You can see this dish and result of observations 6.7 gigahertz. Dates of observations 11, 12, 13 March, because I expected peak of this maser initially in 12 March. I expected detections for all 3 days, but due to errors in peak calculations, this is some shifting. Max peak I detected in 11 March is about 100 Jansky. Lesser peak about 60 Jansky in 12 March. It not detected at all in 13 March. Nothing is about expected velocity. About 6.78 minus 7.5 minus 8 kilometer per second. These results looks like snapshots of pulse fall and length of full time is about 3 days, as expected from Ibaraki. I made data. Next, about possible observations in hydroxyl line. 20-meter dish in Green Bank is I hope is suitable for this purpose. Levels do not exceed 1 to Jansky, and lines of emission is polarized significantly. Both they have 2 lines, 16.5 and 16.67 megahertz, but line 16.65 megahertz is more convenient for observations. Need rather long integration time. 13 minutes is needed, and I think yes, long observation times is credit consuming, significantly credit consuming. Today's credit is not credit on credits on SARA account in Skynet, as I had heard, bills already paid, and in nearest future credits can appear again, but I still have another problem with understanding how to set receivers of this dish, how to tune it. I need some info about how to set integration time, regimes on off track, how to set repeated observations, documents in RAW wiki. Access to documents in RAW wiki needs some more approvals than only registrations. If it's possible to get it, it will be very well. My calculations of minimal detectable peak flux density for this dish for 30 minutes of integration time, 1 kilohertz for resolutions, maximal setting of channels in receiver, expected system temperature 20 Kelvin. This is questions because I am not sure about system temperature. I have made some observations of measures and get system temperature much more. I will talk about it separately, and calculations for minimal detectable peak flux density is about 0.65 Jansky. It is possible to detect with this system temperature in 30 minutes of integration time if system temperature is about 20 Kelvin, I will tell about problems with system temperature separately after this, if you like. But now, if you have some questions, I will be glad to answer.
Dmitri, just one comment. Assuming 20 Kelvin as system temperature is really on the optimistic side. So I have no figure from the 20-meter dish, but comparing to what we have extremely low noise amplifiers, and we achieve something like 35 Kelvin. So I think 20 is something that is probably unlikely that the 20-meter dish there will have such a low system temperature. But maybe somebody who has used it and measured it can tell more.
Wolfgang, I will tell separately about system temperature. Next with this Skynet 20-meter dish. Says 20, 30, 40 kelvins is possible, but I've got much higher system temperature, and it's some embarrassing for me. It's okay.
I think we can. Well, one is the 20-meter dish. We've thanks to Steve Zekas and Tom Jacobs, they've gotten that refunded, and then so we should be able to try it. So we'll get. Maybe we just go ahead and try it, Dmitri, and see if it works. I'm pretty sure they could pick up these water masers. The only question would be is that they do swap out the feeds, and you have to hit it right where they have that feed for that frequency range up. Sometimes they have a different feed up at a different frequency range, and so we just have to figure out what the current feed is. All right. Anybody other questions? Oh, go ahead.
Yeah, I have another question, just elementary question maybe. And in the numbering on this particular maser, you call it G107, initially G107.298 plus 5.639. So can you interpret how that number is developed? Is that G107, is that the galaxy? And then the 298, a particular star in the galaxy? Like you had a slide where you showed the stars and you called it G107.
G107. This is short name for this maser.
For the whole maser. Okay.
Short name. This is not. They say this is young, intermediate mass, young stellar object. Some hydrogen already ignites, as I can see there, but molecular nebula and dust is still there, and we can see a maser from this side, and this is binary. This is maybe binary system rotating. This is very interesting object for maser observations, as I see.
And what does the plus 5.639 mean when they add that to the name?
Bob, that's just the galactic coordinate of the object. So that's where the name comes from. It's galactic coordinates.
But they put the plus just to tell you which direction you're moving.
No, it's a galactic latitude and longitude.
Okay.
And the latitude can be positive and negative.
Right. Okay.
This is equatorial coordinates, right extension and declination. You can see there, and V107, and this is really galactic.
Okay, thank you very much.
And can I tell about 20-meter dish observations and system temperature problem? It's okay?
Okay, well, I think we'll have a couple people researching that here, and maybe we'll have that by Drake's Lounge. All right, thanks. Good work. Okay, Andrew.
Okay.
Sorry. Can you hear me?
Yes.
Brilliant. Sorry, thanks. Yeah, very interesting hearing of all that stuff, and I quite like the picture behind you there as well, Rich. It's quite nice. So I've had a reasonably eventful month in different ways. On Friday night, we had a meeting of the British Astronomical Association, and I was one of two speakers, and I was speaking about the hydrogen line work. And we had I was a bit shocked by the number of complicated questions that came afterwards, but I'm very grateful that Ted was around and was able to answer some of those questions. So thank you, Ted. But what has interested me is that I've had a number of people since that time who have actually contacted me expressing interest and wanting to find out more. So there's quite a lot of interest out there. In addition, on another note, let's just share this screen. So hopefully you can see a chart of a sudden ionospheric disturbance from the 31st of March. Can you see that?
Yes.
For the sake of all you guys over there in America, I've stopped saying the 31st of the 3rd, 2025, because I know you do things the other way around, so I've actually put March in now. And so I managed to pick up this really quite nice M-class solar flare on the 31st of March, and I posted that on the SARA forum. Just as you're passing, I quite like this graph sort of thing, but I've been quite surprised that it seems to have stimulated quite a lot of conversation on the forum with people who are expressing interest again. They're getting involved in SID monitoring, and some people who have had issues with getting their systems working and have been writing to me. So let's just say, Rich, I noticed that you picked up on that and asked for any talks for the Eastern Conference, but it's worth noting that there's a number of people out there who would like to have a go at this type of data collection. What else have we got? So there's the I mentioned the inaugural BAA meeting. That's available online on the YouTube, British Astronomical Association's YouTube account, and you can have a look at that meeting if you want to. And if anybody else, sorry, this is separate from last Friday. There was I set up a hydrogen line group under the auspices of the British Astronomical Association. But I got to say, there's at least as many SARA members taking part as there are BAA members, so it's really a bit of a joint group, really. If anybody else is interested in taking part in that, please just contact me and let me know. And in a second, I will put my email in the chat, and you can use that to contact me. It doesn't matter if you've never done this type of thing before. This is trying to sort of do things like map the Milky Way and demonstrate dark matter. And you don't need anything very big or a very big space in your backyard to be able to do this type of thing or to spend a great deal of money. And it's a incredibly effective project, which, as I've demonstrated, works in reasonably radio polluted areas as well. What else have I got? Oh, there was some discussion I put on the radio, sorry, on the SARA mailing list about my this 1.5 meter dish that I've got, which is this thing here, which is parabolic dish, as you can say, which is, these things are sold on eBay there in the States for about $50, $70, and they're sold. The idea is that you put a kettle or pot at the prime focus point, and it heats it up and boils it for you, and it sort of works quite effectively. But one of the issues with them, using them as a radio dish, is that same mylar coating, which is used to heat up the dish, it's rather difficult to coat it with something to stop it from reflecting the sun and burning out your waveguide. So I've been using spray paint on top of it, but finding the spray paint is a habit of coming off. But if you look at this particular picture on the right-hand side, you'll see that 2 of the 6 petals are a slightly different color. And that's because it was recommended that I try seeing if the mylar coating will just come off if you give it a yank. And indeed, it does come off quite easily. So if anybody else has a go at this, then I would recommend that before you put it together, because it's a right hassle once you put it together, before you put it together, just grab the end of the mylar coating and give it a good tug, and you'll find it'll come off, and that'll make life a lot easier for you. The other thing is this is made of mild steel, so it does rust quite easily. So it is worth coating it with something. And there's some debates on the SARA mailing list about what is the best thing to use, but some form of paint at least, and probably, I suppose, ideally rust preventative paint like Hammerite or something like that, that will preserve your 1.5 meter dish for you. And I'm hoping to present at the Eastern Conference with a mapping exercise done with this particular dish. What else have I got? So I've got that. I've got the M class spare. Oh, right. What have I got here? Hold up. So I put onto my website some instructions on how to use the Skynet radio dish, because I know that we've had a lot of discussion about this on the mailing list. And you can go onto the Skynet website and get hold of these instructions. They're just copied from there, but it just makes it into a relatively easy to access place for anybody who's never done it before. And you can just go through it and see how it works. So that's on my astronomy.me.uk website. I mentioned the inaugural meeting of the H9 group. Oh, another thing, probably the last thing I'm going to say, somebody offered me a 3 meter dish this week. I wasn't quite looking like that, but it was a mesh dish, and I was really tempted, and I was actually planning to go up and collect it on Friday. And then I took a look at my garden and realized that my marriage of 26 years wouldn't survive a 3 meter dish, even if it was free. So I haven't collected it. So if there's anybody else in the UK who wants a free 3 meter dish, I can direct you where to go to get one. And that's me done for tonight. Thank you very much. I will. Where do I get back to the stop sharing?
Okay.
I'm trying to stop sharing if I can find it.
Thanks, Andrew. Anybody got any questions for Andrew? Note on the 20 meter dish access is that if you're a SARA member, you need to request from Steve Zekas permission to get the logins for our account. And then you can use the 20 meter on the SARA account. Other than that, I don't think that you could just go and try to get on the 20 meter unless you were a member of somebody who has an account.
No, I wasn't implying that. And the instructions.
Oh, no, I understand that. I just was saying in general.
Just to say, the instructions on my site do not include the login details. So you would need to have obtained the login details in order to use them.
Right. But if you're a SARA member, and I think we've got it, even an international SARA member now, that used to be just US, but now it could be international, then contact Steve Zekas to get an account and a pass login for our SARA account. Okay. Jason.
Just a quick question, if I could. Yeah.
Go ahead.
Okay, thanks. Yeah, thanks. Interesting on that solar cooker. I was thinking you can get somebody to paint a mural on that big 3 meter dish and have it blend into your yard so nobody will see it, or invisible paint. But I was just talking on the net last night about antennas and coating, and somebody was telling me about this paint, and I have to look for it because it's apparently a paint that you put in gas tanks, petrol tanks, and inside, believe it or not. And they move it around, and he said that that paint was incredible. It's probably I don't know if that's going back a few years. I don't know if anybody's heard of that kind of paint, because he was really adamant. I should have jotted down the name of the paint, but I'm sure an auto mechanic might know about it. But okay, thanks. That's really interesting project. Much appreciated.
Thank you.
Thanks, Stanley. Jason.
All right. So can everybody hear me?
Yes.
Okay. So I don't really have anything new. I've actually been sick the last couple weeks or so. I'm feeling better now, but if you like, though, I could kind of show a repeat of what I showed at the Drake's Lounge Australia a couple weeks ago, just real quick. So let me
Oh yeah, that'll work.
see if I can. Let's see. Where's my? Okay. What's?
You look like you have low bandwidth problems there. We're just getting your little not getting a full picture. Go ahead and try sharing.
Yeah. Okay. Yeah. Let me see here. Share. I think I have high latency. Okay. Here we go. So what I've done is a kind of a before we ran out of credits on our previous 6-month contract on the 20-meter dish. Andrew and I had been talking about spatially mapping M33 or M31, and then I thought, M33 would be actually mappable because the beam size at L band is about 3/4 of a degree, and so there's enough to get a little bit of spatial resolution even on M33. And so I kind of did a proof of concept, and the idea was to actually map velocity information spatially. And what you can see here in this false color image, red is redshift, blue is blue shift, with respect to the average velocity of the galaxy. And what you can definitely see a rotation. And so this was kind of a really a very low resolution, very extrapolated with only a handful of points, just a proof of concept. But I believe that we could map M33 in Doppler as well as M31 and use very short time integrations because it's a relatively bright source for the 20-meter dish. And so I was able to get these points with literally just with 1 second of exposure time. And so hopefully that means that we'll be able to gather several points across the field without burning up a bunch of credits. So anyway, I think I'm going to do a simulation of the M33 with a little bit higher resolution using the lab survey, just to kind of get an idea of what to expect, since we're kind of still waiting for the credits to come online anyway. So that's probably what I'm going to focus on over the next week or so, is doing a lab survey simulation of M33, and in kind of anticipation of getting the credits back up and actually trying it for real. So stay tuned, I guess. That's all I got.
So Jason, is the 20-meter has a raster mode. If you just aim,
I did try that. I actually tried that just to see what it would do. The problem is raster mode only does total power.
Oh, got
as
it.
far as I
Then
can
do
tell,
Doppler.
it doesn't capture spectral information. And so because we're wanting to do a false color Doppler spatial plot, we got to do it kind of, it's more of a manual process because we have to actually capture single points, but because we're wanting to get the full spectrum rather than just total power.
Got it. And do you happen to know what the T-sys for the 20-meter is?
No, unfortunately not. I kind of empathize with Dmitri on that. A while back when I first started playing with the 20-meter dish over a year ago, I was looking for some detailed information on it, and I found that I hit a wall as well, trying to get access to some of the documentation, and I just didn't pursue it at that time. It's probably just a matter of going through the administrative hoops to get access to that wiki, like Dmitri was saying. So that's something that would be worth looking into. I just haven't yet. So
Okay. All right. Any questions for Jason? All right, get better. I hope it's just not that that desert air that's getting to you down there.
no, it's some kind of virus. I'm actually feeling better now. It kicked my butt for about a week, and then it took me about another week to recover, but I'm doing better now. So
Okay, great. Thanks. All right. Does anybody else have an observation that they want to present before I go through the list of people?
It's not an observation, but I have a short presentation that I did for my research group.
Go ahead.
Okay,
You're
thanks
next.
very much. Okay. A little bit of a delay here on my system. Okay. Okay, so in summary, I had to do a presentation on our snow lab. We had a restructuring of our departments. We used to have a physics, astronomy, and we had our snow lab, which is Sudbury Neutrino Observatory, which is connected to another university mostly, but it is connected to ours. So now we're left with the planetarium and the snow lab, which is kind of interesting. I was going to talk a little bit about the system that they have. Presentation is very short. So the main particles here that we're talking about, the alpha, the beta, and the muon, these are traces that you can see in a cloud chamber. And I'm really interested in cloud chambers. I remember in high school, we did this as a science fair, a friend of mine and I, and we ended up using the little glowing numbers from a watch actually to generate some really interesting traces. But we did notice some other traces while we were doing that. So they had a neat video. I'm not sure if you can see that. It's just a GIF, and it's sort of showing they've got a cloud chamber on display when in the place where they're, you can't go down 1.5 miles below the surface, but we do have a display at a science center. And you can actually see the particles in there in the cloud chamber, which is a neat setup. So the neutrinos got 3 flavors. We actually, one of the researchers, the project won a Nobel Prize on figuring out that the flavors of the neutrinos change as they're coming to Earth. And these are quite small. They go through almost anything. Wolfgang Pauli, 1930, he speculated that there could be neutrinos that exist, and he had the physics behind him to there's a picture of him. He's actually lighting up a pipe. You don't see that too often. And in 1953, Fred Raines and Clyde Cohen, they discovered evidence of neutrinos at the Los Alamos National Lab. And the interesting name of the project Poltergeist. So that was really kind of neat. And again, this same picture, they used a hydrogen bubble chamber to detect neutrinos in 1970. So this is later on again. So they're actually getting real evidence on that. And so now neutrinos are for impending. So the electromagnetic radiation coming from an exploding or dying star, supernova, and it includes radio waves and light waves, and the neutrino actually travels faster because it could break its way through all of those clouds, and there's a lot of energy that gets released in neutrinos from a supernova. So this is a picture of the crowd from 1050. This is the one in 1987, 87A. That's a picture from the Hubble telescope. And the supernova is in the center, actually, in that photo. The snow lab. So I'm kind of connected to the snow lab. My great-grandfather worked there. My grandfather worked there. Hard rock miners. pulling out the nickel, and it's from a meteorite that hit about 1.85 billion years ago. It's the third largest meteorite impact crater in the world, and it's 1.2 miles deep. And that's a photo of, I guess that's where they put the main Neutrino Observatory, which is actually it's like a huge globe filled with heavy water, and they have photomultiplier tubes all around it. But this is more about the HALO, and the HALO is a helium and lead observatory and sensitive to electron neutrinos. And they actually, in this particular observatory, not all of them, because they're part of a worldwide network on Supernova early warning system, all flavors will be detected here. They have 80 tons of lead with hydrogen detectors connected to them, and they're moving towards having 1,000 tons. So they want to make sure that they're ready for the event if and when it happens. So this is kind of a long shot for sure, but it's an interesting project. So now they're part of this worldwide network. It's called S-News. I don't know if you've heard of that. You probably have, but after Supernova doesn't happen for a while, you kind of forget about it, and I kind of forgot about it as well. But there is an app, and I did sign up for that app, and we are part of that network in Sudbury. So it's the Sudbury, sorry, not Sudbury Neutrino. It's the Supernova early warning system, and the app's available. They only had it on Android for a while, or sorry, they only had it on iOS for a while, but now they have it on Android. They also have alerts as well. And so, yeah, that's a picture of the app right there. And actually, actually, they maybe I'll play one of the alerts. It comes every Wednesday. I don't know if I can get that to work.
Where's the kaboom? There was supposed to be an earth-shattering kaboom.
So they have a good sense of humor, and they put that in as the alert. It shows up every Wednesday, and you hear that the system is working. So apparently they're trying to get the word out and to actually get a lot of people signed up on that, because the neutrinos will actually tell early, and they're hoping that amateur radio astronomers and optical astronomers will be able to get some good data while they have a little bit of a warning to aim their radio telescopes or telescopes towards that. So let's see, and yeah, and so that's the end of my presentation. I just had done this for a research group as part of my work at the university. So just wonder if there are any questions.
I have some questions, maybe not for presentations. Questions about muons. Do you really see? Is it true that space rays, muons in space rays, can survive in Earth's atmosphere? This is charged particle, lepton charged particle. Electrons, protons do not survive, but I heard that muons can be detected on the ground. Muons from cosmic rays can be detected on the ground. Is this true?
Oh yeah, it's one of my favorite stories about the muons, because muons actually, because they're traveling so fast, they're actually, let's see if I can get that screen. This one's kind of flipping on me. Slowing down my system. Okay, there we go. Yeah, it only lives for 2 microseconds. While a muon only exists for 2 microseconds, but because it's traveling so fast, its time is internally dilated. So it actually lasts a little bit longer, long enough to detect it on the surface of the Earth. Yeah, I'm glad you asked that question, Dmitri, because I meant to mention that, because that's sort of one of my favorite stories from my some of my physics courses that I took in quantum. That this was actually proof that happened.
Okay, thanks.
Yeah, actually, I would add to that too. If you've ever heard of the Cosmic Watch project, where there's somebody at MIT that made these small portable muon detectors that anybody could build for a few $100s. And I remember the guy who designed it took one of these detectors on a commercial flight with him and just recorded data the whole time. And the atmospheric attenuation is there. So some of them do get attenuated in the atmosphere, but most of them do make it through. And it's funny, it's predictable enough that you could actually watch the counts and you could tell when he took off, when he was in ascent, when the plane was cruising at altitude, and when it did its descent and landing, just from the raw counts. Like you could actually see the entire flight pattern just from the raw counts of the muons, because the atmospheric attenuation is so directly related to the density of the atmosphere. So that's another kind of cool thing.
Very interesting. Yeah, air flight. I know I spoke with pilots in the past, and that's when I learned a lot about cosmic rays, because they keep an eye on them. They usually wear a little tag, and if that tag registers too much, then they've got to like take 2 weeks off at the end of the month or something like that to reset their tags, counting for the year. But if we have a supernova, and if somebody has, they actually are reaching out to amateur radio astronomers, and well, maybe they don't reach out to radio amateurs, astronomers, as much as they do to optical. So, but I think there's a lot to be gained from there. I thought maybe it'd be interesting to hear everybody's perspective on what could come out of a supernova in terms of radio astronomy. And maybe even 1987, if anybody did some measurements over. Oh, sorry,
So Stanley, I got a coordination question. If we got a bunch of us in SARA got muon detectors, and I guess we'd get a general count just in normal. But if a supernova does happen, that thing should light up, right? The count should go way up.
Okay, yes, I believe so. Apparently, neutrinos.
We're losing your voice.
Sure.
I think if you turn off you're using a lot of bandwidth on your presentation there.
Smaller than muons are more. I think neutrinos are more difficult to detect than muons, because they're actually they're smaller, so there's a lot of noise. So that's why we have to go 1.2 miles below the surface to sort of get rid of all the noise. And so muons are possibly coming out of supernovas, but I think the neutrinos are still going to get here earlier. So this worldwide network that uses neutrino detectors deep in the Earth will detect probably earlier than muons will.
Got it. But you think if we could detect a supernova with muon detectors potentially? May not be as fast.
Oh, that's a good.
Can I make a statement? I don't believe you would, because the muons that are formed in the atmosphere from cosmic rays are usually just protons and electrons hitting the atmospheric gases that generate the and even some gamma rays that can generate the muons. But again, you just mentioned the muon has a lifetime of approximately 2 microseconds.
Yeah.
So when that supernova goes off, you'll see anything that travels at the speed of light, which neutrinos practically do. So they get here about the same time that the light does. But any particle would definitely not be able to travel at the speed of light. And so any supernova at any significant distance of light years would just, whatever particles come off of it, I don't think you'd be able to detect them on Earth. It would have to be electromagnetic radiation that you would be able to detect.
Well, that's
things like solar flares, that sort of thing, yeah, because they impact the atmosphere and they generate the muon showers. So anyway, I just wanted to make that statement, if it makes any sense.
So we can use a muon detector for solar flares, just like we use almost like the SID detectors potentially.
Yeah, that would be possible, as far as my understanding is, but not not any particles that would be emitted from a supernova. That just it
That
would
makes
never
sense.
get that would never reach Earth in any significant. And of course, it wouldn't be muons because they have that decay. There's also that third particle, the tau, which has the same charge as the electron and the muon. It's it's the three leptons, and the tau even has an even shorter lifetime. It's down into the less than nanosecond lifetime, so that's not detectable by any reasonable instrument other than synchrotrons or particle accelerators. But yeah, solar flares would definitely generate proton showers, electron showers that would generate muons in the upper atmosphere.
So the reason that the neutrinos get here sooner is because they can go through almost like a light year of lead without actually interacting with it. But they get here sooner because they're able to get through that cloud of the explosion of the supernova. So the light takes a long time to get through that cloud, whereas the neutrinos pass right through it. So they've got an advantage, and depending on the conditions, they're talking minutes, hours, or days that it'll get here ahead of time. So that's sort of the hypothesis, anyways, that they can, because they can go through those clouds of match as light. And so, well, I guess this is a test. I don't know if we had it. Did we have any neutrino observatories in the 1980s?
There's one giant neutrino observatory in the South Pole. It's called the Ice Cube, and and that one detects just about everything that gets. And they actually, what they do is they don't look at neutrinos coming from up above. They try to detect the neutrinos that come through the Earth, because there's also neutrinos generated in the atmosphere from cosmic rays, and so they actually look for the neutrinos that get filtered through the Earth, and they look down, and so it's like a whole strings of photomultiplier tubes that are in strings just maybe like half a mile and a mile down into the ice, and they just have a gigantic grid of these strings of photomultipliers, and so because of the timing, they can see the flashes, and they can look whether the flashes are coming from below or above or sideways, and so they can actually calculate the track of the neutrinos that they're detecting. But that's about the largest neutrino detector that's in the world. But there's other ones. Japan has one. There's some experiments now that Fermilab, I believe, are conducting now because there's this weird thing about neutrinos, that there's three types of neutrinos, and they're associated with the leptons, with the electron, the muon, and the tau. And the thing about neutrinos is that they change flavors. One neutrino, as it travels due to quantum sort of fuzziness, can become one of the three. So it might start as an electron neutrino, and by the time you detect it, it's actually a tau neutrino or a meson neutrino. I'm sorry, a muon neutrino. So there's experiments now where the accelerators generate neutrinos, and then there's detectors that are being built now to try to pin down this sort of shape shifting of neutrinos, and also to determine the very, very important factor, which is what is the mass of a neutrino. Theory says that it should have zero mass, but in fact, due to this change in flavors, the calculation is that they have to have a mass, but they're like very, very low mass, which is what allows them to travel at nearly the speed of light. So there's a number of neutrino detectors around the world. But anyway.
Yeah, they're part of that network. So they actually they look at them as a fundamental particle, and sort of like I probably was a little bit misleading in my presentation, because I was talking about the particles in a cloud chamber. They're much bigger than neutrinos, and there's like some confusion sometimes, because you have the electron neutrino, and it's not really, it's just named after it, and it's much smaller. So it's essentially a fundamental particle. Okay, thanks very much. I think yeah.
It's interesting. The southern neutrino detector, one of our SARA members down in Australia has worked there. Andrew Kaikuk, I think I always pronounce his name wrong. But if you guys get on, he's usually on our Drake's Lounge Australias. So if you guys want to quiz him about his work on the the neutrino detector down there, log in there.
I can
Okay.
add a couple of comments to this too for my time, possibly, Rich.
Go ahead.
I've been working with that cosmic ray type system like Jason mentioned, and that was developed by Spencer Axonum, AXAMI at MIT several years ago. But I've got 3 of them here, and I've recently been working on software to collect the data using Raspberry Pi so that I can watch all 3 of them simultaneously. And so I've got code written for both of them. But basically the way it works is it has it's like a cube of plastic that's called a scintillator. And when the muon strikes that scintillator, it creates a streak of light that has a decay time that stretches out the decay time in terms of being able to detect it. And it has a device called a SIPM, which is like a semiconductor device that works like a photomultiplier tube that's very fast, that can collect faint amounts of light. And so you can count muons that are striking the thing. And so your limitation would be the size of the scintillating material that you put together. And it's using a Adreno to Nano to do all the collection and the information. And so he's right, you can put these together for $150 to $200. I'm not sure who's producing the boards if you want to get a hold of them, but I've got 3 of them, and my dream is to stack 3 of these up and put this online with some of my other data collection stuff and have it collecting the muon counts that they pick up in time. But I'll publish this information on GitHub when I get it done in case other people want to use the code and things that I produce here.
Well, thanks, Bob. That's good stuff. Tom, you got your hand up.
Sorry, Rich, can I just, sorry, after Tom, yeah.
Go ahead, Tom. You're on mute.
Okay, yeah, okay. What I wanted to comment about neutrinos, excuse me. When supernova 1987A exploded, there was a single neutron detector experimental, I believe somewhere quite deep in an old abandoned gold mine in South Dakota, that actually detected neutrinos from the supernova. And it was a very lucky event for them to do it because they were only operating about 12 hours a day. But they did detect, they detected either 7 or 9 neutrinos from the vicinity of the Large Magellanic Cloud. And people have decided that that is the 0 time, or the time of core collapse, for the supernova 87A. So, and of course, like I say, that was back when they were just beginning to look at neutrinos, and they were about to discover the neutrino deficit from the sun, because mostly they were trying to look at the sun. So they were observing the neutrinos that were coming all the way through the Earth. And they got lucky in that they, like I say, they had 7 or 9 events in the detector. So that's what it is. And the neutrinos are created at the core collapse, and they can propagate out almost instantaneously, where the light has to work its way out through the layers of the gas, the plasma, and then make it to the photosphere. And that takes several hours according to most theoretical computation. And that was my comment here. And I guess I'll go back and let other people carry it on.
Okay, thanks. Andrew, you're next.
Yeah, if I could just share something. It's about the Cosmic Watchdog program. So this is, I give a talk on this. This is data from the Cosmic Watch team at MIT in relationship to that height data. So 2 major experiments they've done. One is collecting data from around the world, including on a flight at about 30,000 meters, which you can see on the right-hand side, and you can see there's a clear correlation between a lower count rate the higher you go, The one on the left-hand side is actually in a high-rise building at different heights. So there you've got both the combination of elevation plus the I suppose the amount of concrete between you and the upper atmosphere. It's worth mentioning that with these, so there's just a diagram showing the as it's just been shown, the sort of flash out of what you actually get inside one of these detectors. Say it's a kitchen foil and black electrical tape that's cleverly used to optically isolate the scintillating block. There's this concept called coincidence measurements, where you use two of these detectors, basically one on top of each other. And this is because muons are generated by surrounding rocks and other things around us. And these detectors will actually pick up other types of radiation, such as alpha and beta particles as well. So it's not just isolated to muons. So what coincidence does is it says that the only counts it will include are those that went through the top detector within 30 milliseconds of the count being picked up by the bottom detector, and therefore picks up the ones that are only coming from above, which tends to want somewhat to isolate the types of particles down partially. It's not complete isolation, but the Cosmic Watches teams, and I've spoken to Spencer about this, and his argument is that this is all a relative measurement anyway. So as long as what you get out of surrounding rocks, etc., doesn't change too much, then there's probably some validity to the results that you're getting. They themselves used a little bit of radioactive rock on top of the detector as a test measurement to show that the further you went away from the case, it dropped off. And so it's obviously it is I forget what radioactive uranium produces, but it just shows a number of radioactive particles. Sorry, this is my actual setup. I've got two of these detectors. Mine were produced by the UK Radio Astronomy Association here in Britain. This is a charity which produces equipment for radio astronomers with very little profit involved, but virtually no profit at all, mostly using volunteers. So the ones that I'm using at the moment are like the ones that have just been shown. They're ones based on the Cosmic Watch program with the Arduino Nanos in them. This shows data being collected as on their website that they provide as one way of collecting the data. And just to show that I decided to use this radiation device, i.e. the banana, so we can measure the number of bananas on top of my detectors and work out what happens to the muon count. And you can see there a relationship between the number of bananas and muons. And finally, just to say, and probably importantly, so the UK RAA was producing the Cosmic Watch muon detectors, and they produced two different types, either one that was fully made up, or you could put up by just the components and put the board together yourself. But in fact, they are just about to launch a revised version, which they call the Muon Nano or something like this, which is, no, sorry, Pico Muon it's called, sorry, the new project. And that includes within one box, two detectors in coincidence at a set distance apart. The two scintillating blocks will be 2 centimeters apart. It will use a Raspberry Pi rather than Arduino Nano, which overcomes some of the RAM limitations which are on the Arduino Nano, and also some of the speed limitations that are on that device, and gives a much better range of options in terms of what you can do with it. In particular, you can actually record data straight to an SD card while still being able to look at the little screen there, which in these Cosmic Watch devices, because of lack of RAM on the Arduino Nanos, you have to load up a different compiled version of the software if you want to save to SD cards from the version that allows you to see the screen. The other problem with the existing Cosmic Watch one is you don't have any option to turn the screen off. And if it's left turned on for several months on end, which is exactly what you want to do with it, the problem is that the screen dies on you. And finally, there's one other big issue with the Cosmic Watch muon detectors as they stand at the moment, and that is simply lack of software, has just been alluded to. You can use the website. I found that the website has a habit of crashing on me, whether that's the website itself or whether it's my local network, I don't know, but then you can end up losing all your data. So I end up saving it on my computer, but there's no readily available software to process and display the muon data. And Ted's been helping me out with this, trying to write some scripts under Easy Radio Astronomy that will do that display. And if we can get that working, we'll share it with everybody else. But at the moment, it doesn't exist, whereas the Pico muon system that UKRAA are due to produce, they're going to produce some software to go with it as well. Okay, thanks.
All right, good stuff, Andrew. Thanks. Okay. Anybody else have any big presentations or observations? And then I'm just going to go run through. We got 20 minutes to run through everybody for quick comments. Okay. Don't hear anybody. Preston.
Hello. Hello.
Go ahead.
Yes, I had a small presentation on solar eclipse.
Okay, go ahead. Do it.
It's a few minutes, huh?
That's fine, Henry. Go ahead.
Let me see. I don't know why it's not doing. Trying to get the first page.
So, by the way, Henry, where are you located?
I'm in Prague, Czech Republic.
That's right. Okay.
All right. So, good afternoon, good evening. I'm still a new member, in SARA. Sorry, but I have no prior experience in radio astronomy. Only a few years of beginner's practice. I made a first email in November last year, and then I made a quick appearance in the January Radio Astronomy Observation Party. I was encouraged to make presentation. So during the last eclipse, I was able to record some measurements, and let me share them with you about the eclipse. So, is it working? Yeah. First, the local parameters. Location is near Prague. You have the latitude, longitude. The eclipse was expected to last about an hour and a half, from 11:30 to 1 o'clock, and the occultation was 20%. Not like in Western Europe. In Central Europe, the sky was cloudy. Okay, so I have one picture here with the antenna there, and this is the sun there. And if you make a zoom, you see that you got almost a perfect disk, although this picture was taking 20 minutes inside the duration of inside the occultation, but it's not possible to see a dent. Let me talk to you briefly about the observatory. I have a reflector, which is a plain geodesic paraboloid, 2 meters, 0.25 f/d. It's got a dipole with cavity. It's mounted on a rotator. The LNA is from Australia. In the receiver box, I got a Adam Pluto for SDR, and the box in which it is covered is a PID temperature control. And then I got a laptop to control all that. On the next slide, you'll see a picture of the antenna. As I described, 2 meters, 0.25, and then is the dipole here, and then the rotator there. On the next slide, I have gathered the equipment. You have the controller for the rotators, a DC unit, the receiver here with the SDR inside, and the computer. This is the dashboard. This is what I'm looking at when I take a transit, which is what I do mostly. I have the little application which drives the rotators. I got the sky chart radio astronomy application to know where I'm looking at. And then I have a program here in MATLAB, where this is the program that commands everything. And this is the picture of the signal, which I'm looking at live as it goes. So I was, before I started the measurement of the eclipse, I was, of course, like everybody, hoping for a nice dip showing the restriction of the sun, with two horizontal bars on each side before and after the eclipse. But I was a bit careful, and I wanted to have some margin before and after. So, in fact, for an eclipse that lasted 90 minutes, an hour and a half, I made an observation of 4 hours. So on the next picture, you'll see this equivalent here, but for the sun. So when you look at this picture very quickly, you can see the dip. So you say, I got it, fine, happy. But then I started to worry a little bit about what are those change here before the start of the eclipse, and those after. I was not sure I had a dip that was enough. Maybe there was, because the sun being low, you know, I thought maybe I was catching some of the ground. So after, also noticed that the dip you see here started at about 11:15, when the eclipse was to start at 11:30. On the other hand, here it's supposed to stop at 1 o'clock, 1300 hours, and it did. So I was happy about that. But what are those things here? What are those things there? So what I did, first I noticed that, and I knew about it before, that this part here is because of the roof top of the neighbor house. So the antenna is catching a mix of ground, if you will, by the roof and of the sun. And the same here from the other house. So I just have this conveniently, this part that is able to show the eclipse. So to make sure I was looking correctly at the findings, I decided to repeat the observation the next day in exactly the same conditions. So I did not change the time, the duration, the calibration, the gain, the sampling, all that stayed the same, except, of course, for the moon, which was the next day not there. So on the next slide, you will see what happened the next day. You can see we still have these bumps here, these bumps there, but then instead of having a dip, we should have had a flat line, which was the sun, but starting at 1 o'clock, I had a bit of a excursion of the gain upwards. You will notice that on the previous slide, we started at 10, finished at 2. The next slide, of course, we had a change of hours. Okay, so I started at 11 for 10 and finished at 3. The temptation was, of course, to put to superimpose the two curves. And this is where I found out that this hour before was very useful, because it helped me to calibrate, so to speak, the two curves in superimposition. So here I had between the 29 and the 30, I had a delta of 1 hour for change of time, 4 minutes for the regulatory difference in the time, the duration of the day, plus 2 minutes because I started late. So that is 6 minutes. And on the next slide, I did the superimposition of this on an Excel sheet. You can see here the 6 minutes. You can see that the curves are nicely fitting, especially at the beginning. So I was comfortable now that the superimposition of the curves was correct time-wise and horizontally and vertically. So I could see that the eclipse indeed started at this point where the two signals start to diverge. Unfortunately, it was still 10 minutes earlier than the 11:35. I still don't know why, but it seems like it started 10 minutes earlier. After that, you can see that there's a difference creating. Then there's an excursion of unexpected excursion of the gain upwards, when in fact it should have continued straight, and it should have met here at this point, which was exactly 1 o'clock. So this is what I explained here. So you see, there was some definitely sure that it was an eclipse. I could see it. I could agree on the beginning and the end, but there was problem with the gain, and you can see it here also. I still don't know why there was a gain issue, but here it was 0. The delta increased, should have come down to 0 at 1 o'clock, but continue upwards. So after I did that, I was tempted to see whether the delta here was related to the degree of occultation. You will remember in this part of Europe, in Prague, it was 20%, 19.9. So I did not know exactly how to do that. In fact, I submitted to your checking to see if you can confirm or tell me I made a mistake. But I simply consider taking this difference here and divided by this value, which was the sun without the eclipse. But of course, to be fair, I should not take this value because I suspect the gain to be higher than it actually was. So I would think that this was the value of the sun the next day, and this was the value of the sun during the eclipse. So my difference is actually this one. So when I did that, instead of 19.9, instead of 20% occultation, I found always between 10 and 12. So I was not very happy about that, but I had to accept it. There was a difference until I thought about looking at the solar flux issued by the Canadian Department of Natural Resources. Actually, I used that value for the 29th. The sun was at 155 SFU, okay? And the next day, I initially thought it was the same, but it had increased. It had increased by 10%. Instead of being 155 SFU on the 29, it was 170 the next day. So when I did my very, very quick dirty calculation, on the 30th, it was 1,440, which I could read on the curve. But because everything was based with 155 SFU, I added by 10% to obtain this value. The solar flux on the 29th, however, himself was made at 155. So this is the value I got. And the difference is the percentage of calculation was the difference of those two divided by this one. I got 16.7% instead of 19.9. Voila, that's it. That's it for me. It's a quick one. If you see some mistakes or some things that are not right, I would be very, very, very happy to hear from you. Thank you.
This is great, and we're running out of time a little bit. But the other thing to look at, if you can measure SFU with your telescope, if you keep monitoring it and then compare it to the sunspot numbers, they're supposed to be you can correlate them. Higher SFU is more sunspots, and so if you look at their, I think it's the Canadian Solar Telescope publishes this, and the GOES publishes some of this SFU versus sunspots. So if you want to count sunspots with your radio telescope, you look like you have a good ability to do that with your setup.
Okay, thank you.
All right. Let's see.
Any other questions? Or okay.
Okay. Excellent, Henry. Thank you. You're. Let's see. Anybody have anything real quick? We got 4 minutes, and we're not going to get to everybody. So I could do one more big presentation, 4-minute presentation.
I'm in here. Okay, I had a comment on his solar eclipse measurements. Back on April 8th of last year, I tracked solar eclipse at 12 gigahertz. And one of the things that's a very useful technique is to aim your antenna at cold sky and then aim the antenna at the sun and go back and forth, because that way offset drift to your instrument will show up. And you can also put a black body radiator in front of the antenna. So you go 3-step thing, repeat cold sky, black body radiator, sun. Repeat that over and over again. Now you have a step function that you can help sort it. I did find that useful at 12 gigahertz for whatever that's worth.
Okay, thank you.
Another comment. What frequency were you at? Was that at 1420 megahertz or what?
Yes, it was 1420. But you know, all this was done in full power. Okay. There's no the frequency. The frequency is just the favorite frequency of the SDR, but with a band of 4 mega. But it's a full power. I take the whole signal.
Yeah, 4 megahertz should totally blank out any background hydrogen, because it's such a narrow bandwidth signal. So 4 megahertz, hydrogen essentially goes away. You have a very good total power instrument.
Okay.
All right. Anybody wants to log into the SARA Eastern Conference, June 7th to the 11th. Go to the SARA store, the SARA website, go to the SARA store, and there's an online conference. So you can log it, or you can pay for your online conference. We still have the ability to go physically there. I think we're starting to run out of spaces at the, I'm not calling it the dorm, but the residence hall. So if you make sure that if you go there and you don't have residence hall room, that you find some other space. You know, they've got some local motels and Airbnb stuff on the outside in West Virginia. Okay. Any final comment? All right, excellent. We got the full YouTube video full of great presentations this month. Drake's Lounge is in 2 weeks, same time, and I'll be glad to see you guys there. All right, and the journal will be out on the at the end of the month. Okay, thank you, everybody.